Hi, we're going to look at a partial fractions integration example. All right, so here we have a rational function that we're going to integrate, and so you should go through your little mental checklist thinking through how to integrate this. So you might start by thinking about, do I know this antiderivative? No, this is not one that you're supposed to have memorized. Could I do a u substitution? It's possible that you might think about letting u equal the denominator and then think through if you have the right expression for the du. Your du would be 6x squared plus 6x minus 2 dx. And so I can't really make that work with what I have on the numerator here, so u substitution is not the way to go. Integration by parts would require that I factor this into two expressions, one of which gets simpler or at least not more complicated when I differentiate it, and the other one that gets simpler or at least not more complicated when I integrate it, but that's not really possible to do with an expression like this. So then noticing that we have a rational function, you should go right to partial fractions. So for partial fractions, you want to start by factoring the denominator. So I'm just going to write under the denominator of the original expression over here, do a little scratch work and factoring over there so that I can get ready to do my partial fractions. Alright, so I'm going to first notice that there's a common factor of x that I can factor out. So if I factor out a common factor of x, then that doesn't go away, it's still out front. But then I'm left with here a quadratic trinomial that I can then factor. The first factors have to multiply to give you 2x squared. So 2x and 1x would be what we would need to make 2x squared. The last factors are going to have to multiply to give you negative 2. So I have a 1 and a 2, one of them positive and one of them negative, and I have to make sure that when I think about FOILing that out that I'm going to get the right middle term. So it looks like a plus 2 in the back end there and a minus 1 in the middle. When I FOIL that out, I'll get the right term on the middle there. Okay, so that's just my little scratch work for factoring the denominator, and then we can set up partial fractions. I'm going to get rid of this u substitution that did not work here. Okay, so I cleaned that up a little bit so that we can set up the partial fractions here. For this partial fractions, I have three distinct degree 1 factors, x, and then 2x minus 1, and x minus 2. So when I set up the partial fractions here, I'm going to think about this with having distinct linear factors in the denominator. So my three denominators that I'm going to have here are x, 2x minus 1, and x plus 2. Those are all degree 1 polynomials. The numerators will be degree 0 or constant polynomials. Okay, so there's the partial fraction set up, and then I want to set that equal to my original expression. I'm going to write that with the denominator in factored form though. Okay, so then at this point you want to just multiply through by the common denominator. So our common denominator is x times 2x minus 1 times x plus 2. And the whole point of multiplying through by that is to clear the fractions. So when I do that, when I multiply that denominator to the first term that I have over here on the left side, the x factor will cancel with the x factor I'm multiplying by, and I'll be left with a times 2x minus 1 times x plus 2. And then when I multiply all of that times my second fraction, the 2x minus 1 factors will cancel. So I'm going to be left with b times x plus 2. And then when I multiply times the last fraction on the left side, the x plus 2 factors will cancel. So I'm going to be left with c times x times 2x minus 1. And then on the right side of the equation, the entire denominator will cancel, so I'll just be left with the numerator, x squared plus 2x minus 1. Okay, so then at this point you have to figure out what the a, b, and c are. So there are a couple ways to do that. We looked at some problems where we set up a system of equations. We also looked at problems where we plugged in convenient values of x. That's what I'm going to do here, plug in some convenient values of x. Either of those methods will work every time. It's just kind of a matter of which one's easier certain times and whether you've done enough steps to get what you need to do. Okay, so I'm going to start by plugging in x equals 0 as a convenient value of x. When I put in x equals 0, that's going to make my last two terms here, the b and the c term, go away completely. So I'm just going to be left with my a term here. So there's a lot going on here, so I want to be really careful when I plug in x equals 0 that I don't miss anything. So that first factor will be -1, the second factor will be 2, and then on the right side of the equation I'll have 0 squared plus 2 times 0 minus 1. So that equation becomes -2a equals -1, or a equals 1/2. Alright, so there's my a value. And then let's see, to get the x plus 2 factors to go away, I'm going to plug in x equals -2. That'll make my x plus 2 factors go away on the left side of the equation. So those two will disappear. And then I will have c times -2 times 2 times -2 minus 1, so that factor will be -5 equals, and then on the right side of the equation I want to make sure I don't make any sign errors here, so I'm going to write this out carefully. I just plug -2 into the right side of the equation. Alright, so on the left it looks like I get 10c, and on the right side I will have 4 minus 4 minus 1, so -1. So c is -1/10. Okay, so let's figure out how to make the other factor go away. So the other factor that I have here is 2x minus 1. So it looks like if I plug in x equals 1/2, that will make the 2x minus 1 factor go away. Alright, so my 2x minus 1 factors will go away, so that whole term and that whole term will disappear. And so I'll be left with b times 1/2 times 1/2 plus 2 is 5/2 equals, and then 1/2 squared plus 2 times 1/2 minus 1. So it looks like I get 5/4 b equals 1/4 plus 1 minus 1. Those cancel. So 5/4 b equals 1/4. Multiply 3 by 4/5, and I'll get b equals 1/5. Alright, so that's all my scratch work, my algebra for the partial fractions, but the whole point of that for this problem was so that I could do some integration. So I'm going to have to scroll up so that I have some space here, but I'm going to go back to my original integral now, and instead of having it as one big rational expression, I'm going to use what I did to rewrite the left side as a sum of rational expressions. Okay, so we'll scroll up so we can do that. So from our partial fractions setup here, I had the a over x, so I'm going to write that 1/2 times 1 over x instead of putting a fraction on top of a fraction, and then plus b, our b was 1/5 over 2x minus 1. So again, so that I don't have a fraction on top of a fraction, I'll write it like that, and then minus 1/10 over x plus 2, or times 1 over x plus 2 dx. Alright, so there's my original integral written like that. Whether you write it out or think it through like this, you want to think about probably separating that into separate integrals. So I'll have 1/2 times the integral of 1 over x dx plus 1/5 times the integral of 1 over 2x minus 1 dx, and then minus 1/10 times the integral of 1 over x plus 2 dx. So these are now simpler integrals than I started with. Alright, so I need to think about how to do each of those integrals. So scroll up here and think about each of those. Alright, this first one is one that I know. That's one we're supposed to know. The second one is not one I know, but it is one I can do a little u substitution with. So we'll let u equal 2x minus 1 on that one. Du then is 2 dx, and we'll need to deal with that 2 there, so I'm going to divide that over to the other side. 1/2 du equals dx, and so for that part of the integral only, I will have 1/5 times the integral of 1/2 times 1 over u du, and so then that's an easy integral to do. For the last integral here, different u substitution, so I'm going to use w here, just so we don't have the same u here. X plus 2, and then dw is dx, so that last integral is going to become minus 1/10 times the integral of 1 over w dw. And then those are easy to do. So all that stuff that I wrote in red there is not necessarily stuff you would need to write out. If you want to write it out, that's fine. I was kind of thinking about each integral separately. The easy u substitutions like this, I'm perfectly fine if you do those in your head. Okay, so for the second integral here, I have the 1/5 that was already there, and then times the extra 1/2 that I get from doing the u substitution, and then ln of absolute value of u. My u is 2x minus 1. And then the last integral, I'll have minus 1/10 times natural log of the absolute value of w. W was x plus 2. And I need a big old plus c at the end. I can probably go ahead and simplify the 1/5 times 1/2 in there. Your textbook may also use some properties of logarithms to rewrite this in a different form, and that's fine if you want to do that, but I probably wouldn't. Alright, so there we go. Alright, so that was kind of fun. So that was an example with 3 distinct linear factors, and thinking about what I had to plug in to get rid of some of those factors this time was a little bit harder. Alright, next video is going to be with some different kinds of denominators, so check that one out too.